Hello, class. Welcome to the next segment in Lecture 23. And in this segment, we're going to take a look at a highly idealized synoptic scale setup that we would look for if we were to get, say, something like a tornado outbreak occurring. And this is going to primarily focus on what we would see in the plains. There are actually several different potential setups that can favor outbreaks in other parts of the world, like in the southeastern United States. But primarily, what we're going to focus on is what you would typically see on a potential big tornado day in the southern plains or the central plains. So let's go ahead and dive right into it. So here we're focusing on the synoptic scale setup. We're not focusing on the stuff that you would get from soundings. We're just looking at big picture features in the atmosphere that might be a signal that we could have an active tornado day. So the first thing that we're going to take a look at is the surface pattern. And ideally, what you want is a cyclone that's slow moving. If you have a slow moving cyclone, then that means you're going to have stable air that's also going to be moving more slowly, which means your thunderstorm updrafts are not going to be undercut by stable air. But ideally, in the plains, you also want a dry line, and this is the reasons why you want a dry line for a tornado outbreak were highlighted in Lecture 20 when we discussed dry lines. And I'll go ahead and repeat some of those points. So again, dry line. The vertical motions along a dry line tend to be weaker, which means you're going to have a much better chance of getting isolated thunderstorms, which have a much better chance of becoming long-lived supercells, which are capable of perhaps producing strong to violent long-track tornadoes. And again, one of the other things that we like about dry lines for tornado events is the fact that they regress westward after sunset, unlike a cold front, which will accelerate forward after sunset when radiative cooling starts to take place near the Earth's surface. In the case of a dry line, it will actually regress westward, which means it will be bringing stable air away from the thunderstorm updraft, as opposed to a cold front, which will be bringing stable air under the updraft, which is not what you want to have. You want to have nice, long-lived surface thunderstorms that are surface-based throughout most of their life cycle to get a potential tornado event. And also another reason, well, we'll come back to this a little bit later on, but ideally what you want to have is a due south wind at 850 millibars and a fairly intense wind. So again, we talked about the role of the low-level jet. Ideally, you want a nice 30-plus knot wind, due south wind at 850 millibars, which gives you a low-level jet that is sufficiently strong to produce low-level rotation or the potential to produce tornadoes. And also you want ideally a lot of directional shear in the lowest 1 kilometer or so. And that would typically be, say, a southeasterly wind at the surface going to due south at around 850 millibars and then maybe going due west at around 500 millibars. And in the plains, you don't want a southwesterly flow at 850 millibars because that's just going to bring hot, drier air over the warm sector, and that's just going to reinforce the cap. And if you reinforce the cap too much, then you might not get any thunderstorms going up at all. And again, we talked about the role the cap plays in a previous segment of this lecture when we talked about the elevated mixed layer and the unique topography found in the plains. So that's ideally why you want a due south 850 millibar wind as opposed to a southwesterly 850 millibar wind direction. And then at 500 millibars, ideally you want something that's either due west or maybe west southwesterly. And if you get especially a strong flow pattern at 500 millibars, then you're much more likely to get a dry line bulge. And again, we talked about this in Lecture 20, where if you have a dry line bulge, the directional shear is much more enhanced north of the bulge, which gives you a better chance at more intense supercells capable of producing more intense long-track tornadoes. And the other reason why you want a flow pattern that looks like this is because you can see how the dry line and the wind vector are perpendicular to each other. And we'll talk about this in greater depth in the final segment of this lecture, but if you've got a boundary and a wind vector that are perpendicular to each other, then that gives you a much better chance of producing isolated thunderstorms. It doesn't guarantee that you will get isolated thunderstorms because you could have too many storms forming along the boundary, in which case they all crash into each other and basically merge into a massive squall line. But if you've got weak vertical motions and a nice flow pattern that's perpendicular to the boundary, that gives you a better chance of producing isolated thunderstorms, which in turn have a better chance of becoming supercells. And of course, supercells typically produce the stronger and longer-lived tornadoes if the rest of the environment is favorable. But another feature that we typically look for is something that occurs in the jet stream. Ideally, so we talked about jet streaks in some previous lectures, but we primarily focus on a straight jet streak. Ideally, for a tornado event, you want a nice cyclonically curved jet streak. And you'll take a look at this in your synoptic scale classes, but you can actually show from sort of a mathematical standpoint that the vertical motions in the right exit region or the left exit region of a cyclonically curved jet streak are much more enhanced. This curvature enhances the upward motions in the left exit region and the downward motions in the left entrance region. So this will enhance your upward motions if you have a cyclonically curved jet streak in the right position, and those enhanced motions will lead to the development of a more intense surface low, which will do a couple things. One is it will enhance your directional shear by increasing the intensity of the wind field, so you'll have a better chance of getting a stronger low-level jet. But this will also bring more moisture into your warm sector, which will lower your LCL heights, which will lower your cloud bases, which again have a better chance at producing more intense tornadoes. And this is just a big picture synoptic scale setup. You can get tornado events from setups that are not like this. This is just more of a textbook setup, but not all big tornado events are going to follow this setup here, but most tornado events will follow this setup. And also you want to make sure that the other factors that we talked about in segment 2 are also in place if you're going to say that there's going to be a big tornado event. But that's going to do it for this segment on the synoptic scale setup for a tornado event. And in the next segment, we're going to do the same thing, but we're going to focus on the synoptic scale setup for a derecho event. So with that, I will see you all in the next segment.